Buenas, corillo de curiosidad científica. Mi nombre es Agustín Valenzuela, con ustedes nuevamente otra semana más. Y esta semana es una semana muy especial porque voy a tener una conversación con Daniel Whiteson. Estoy haciendo este intro primero para que sepan que esta conversación es en inglés todo, casi todo, porque Daniel Whiteson es un físico de partículas, pero él no habla casi español, él habla muy poco español. Bueno, creo que habla más de lo que yo pensaba, pero anyway, la conversación mayormente en inglés, pero no se apuren porque después de esta conversación yo haré otro capítulo, ¿verdad? Trayendo esta información lo más resumida posible de toda la conversación que tuvimos. Y nada, espero que igual se disfruten la conversación. Él es tremenda persona y aparte de físico, tiene un montón de otras cosas que hace, incluyendo que tanto Jorge Chan y él, que es Daniel Whiteson, tienen este libro que se llama We Have No Idea. Y pues disfrútense en esta conversación nuevamente en inglés para este podcast que es en español, pero vendrá el resumen de la conversación para que todo el mundo se deleite y aprenda de esta conversación. Recuerden seguirme a mí en Curiosidad Científica Podcast en Instagram ¿verdad? Recuerden también buscar a PR Sin Filtro. ¿Quién es PR Sin Filtro? Es la compañía que te va a ayudar a mejorar tu programa, tu podcast, tu intro, todas esas cosas maravillosas. Y tiene esa gama de podcasts que como café en mano, conversaciones brutales, a veces muchas cosas, ¿verdad? De autoinspección y cosas que te ayudan como persona, individuo y conversaciones brutales, como ya dije. También busquen a el Pocket, que es un programa que te ayuda con tus finanzas. Y pues, este que está aquí, con curiosidad científica, su host, Agustín Valenzuela. Ahora, sin más preámbulo, vamos a la conversación con Daniel Whiteson. Espero que se la disfruten. Como dice Marie Curie, en la vida no existe nada que temer, solo cosas que comprender. Recuerden, Cory, buscar la manera de aprender que más le divierta. Neil deGrasse Tyson dice: nadie que es curioso es tonto. Las personas que no hacen preguntas permanecen ignorantes del resto de su vida. Y para ustedes, esto es curiosidad científica. Buenas, corillo de curiosidad científica, con ustedes el día de hoy tengo de invitado a Daniel Whiteson. Vamos a hablar con él sobre muchas cosas, pero sobre todo sobre lo que más quiero saber es sobre las partículas. So, Daniel Whiteson con nosotros, with us. Daniel, how are you doing today?
I am good. I am good. I hope all of your listeners out there are safe and healthy.
Yes, yes, for sure. Um, that's one crazy thing. Like, I believe, like in these situations, like people should, it's kind of hard, but at the same time, sometimes you don't really have time to read something or to explore another things, and sometimes this is not really as bad as could be. Sometimes it can give you a little bit more to your imagination or your things that you left behind at some time ago. But anyway, Daniel, what's going on with you? Tell us a little bit about you.
Well, I'm a particle physicist at UC Irvine, and I smash particles together to try to figure out what is the universe made out of and what is dark matter and how does everything work. I see the universe as a crazy sort of bonkers puzzle that we need to solve, and we're trying to figure it out one piece at a time. And we're here during lockdown, everybody's working from home. But as you say, it's a good time to be thinking about things deeply. And so I think we can both sort of turn in and think about what's in our minds, the questions we have, and also turn out and think about what's out there in the universe.
Okay, that's great. Uh, let's start with that. Let's start with smashing stuff together, because in your book, especially, you start your book talking about the building blocks. And can you explain a little bit? Because before we used to think like it was fire, water, dirt, and whatever air, and then after that things move a little forward, and then it's like, okay, we have a periodic table. what is going on after that periodic table?
Yeah, thank you very much. I had a lot of fun. I wrote this book with my friend Jorge Chan, and the book is called We Have No Idea. And the main message of the book is that science doesn't have everything figured out. I think because we have made a lot of progress in understanding the universe, people might think, oh, science has most everything understood, and there are just a few details left to figure out. And the point of the book is that the exact opposite is true, that we're just beginning to understand what things are made out of. And so, as you said, we started thousands of years ago, people trying to figure out, like, what is the stuff around me made out of? These rocks and these bushes and these people and this sky? And, like, is there a way to sort of unify it, to understand all of it in terms of something simpler? And that's a crazy idea, even to imagine that the different things you see around you could be made out of smaller, simpler things. And you know, the first ideas people had, air, fire, water, those are now, it seems like simple, silly ideas, but it's really a profound concept to say, I can explain all the complications around me in terms of a simpler set of objects. It's a really deep idea, and we don't know why it works. You know, fast forward a few hundred years or a few thousand years, and we have like the periodic table, as you said, which we can explain anything, right? And this is scientific. It's not just like speculation like the Greeks. This is real science, right? You can make anything you've ever eaten can be made out of 100 basic building blocks. Anything I've ever eaten, anything any human has ever touched or seen or thrown at each other, made out of the same 100 building blocks. And it's sort of crazy to imagine that that's the case, that the universe sort of works that way. And now we dove further into the atom, of course, to understand what it's made out of. And we have a proton and a neutron in the nucleus surrounded by electrons. And inside the proton and neutron, we have quarks, up quarks and down quarks, which are these funny little particles. But the end of the story right now is that we have up quarks and down quarks to make protons and neutrons, and then around them electrons. And that means that you just need three particles, up quarks, down quarks, and electrons, to make any atom, to make anything, which means anything is made out of the same particles, right? Me and you and hamsters and lava and stars and chocolate, right? They all have the same recipe, up quarks, down quarks, electrons, and in the same number, right? Like I'm made of the
Yeah.
same number of up quarks, down quarks, and electrons as you are. The only thing that is different from me and you is how those little pieces are put together. It's like Legos, right? A Lego dinosaur is the same as a Lego spaceship. It's the same pieces, just arranged differently. It's incredible what we've learned about our universe just from trying to take it apart.
Wow, man, that's what blows my mind too. Like pretty much everything is made out of three stuff, and there is a bunch of particles. Like all the time we're talking about like the muon, tau, and whatever these other particles, but in a sense, like especially those ones. Like let's talk about muon and tau. They're pretty much an electron, but they are heavier. Why is that? What's the difference?
Yeah, great question. I wish I knew the answer to that question. But you're right. It's on one hand we can explain everything we're made out of in terms of these three particles, but then there are other particles, right? I mean, me and you and chocolate cake, we're made out of these two quarks and electrons. But sometimes in special situations you find these other weird particles that are not made of up quarks, down quarks, and electrons. They are their own weird fundamental particles. And about 70 years ago, people thought, oh, we're mostly understanding things. We got the proton, the neutron, the electron. We got to figure it out. And then somebody found the muon, and we were like, what? Who ordered the muon? We don't need that craziness. So we mostly were figuring things out. Don't confuse us. And it doesn't make any sense. Like, why is the muon? Like, that's a basic question nobody knows the answer to. Like, the electron and the muon are identical. They have the same spin, the same charge, they interact almost the same way. The only difference is the muon is heavier by a lot. So why does the electron have this heavier version of itself? We have no understanding. And then there's this another one, the tau, is an even heavier version of the muon. Why does that exist? We don't know, but what we do know is that it's a clue, right? When you look at the periodic table, for example, you see patterns. And you know that those patterns tell you something. They're clues to how to get down to like a deeper layer of reality, how to like peel back the mystery and discover the truth. And now, of course, we know that all the structure of the periodic table is in fact telling us about how electrons fill their orbital shells, and that makes something metallic or not or whatever. In the same way, we look for patterns in our current particles, and we think that those are clues that tell us how things are organized underneath. For example, maybe electrons, muons, and taus are not tiny little point particles. Maybe they're actually made of even smaller particles, and you just arrange them in different ways to get electron, muon, and tau. And in 100 years, people will look back and be like, man, that was so obvious. How couldn't they couldn't see it, right? And so I think that these are clues to basically future Nobel Prize winning discoveries we just haven't made yet. And these questions are tantalizing. And that's frankly why we wrote this book, because there's so many of these really, really basic questions nobody knows the answer to, that I think are, the hanging thread that's going to lead to an incredible discovery.
Yeah, sometimes I try to fantasize that I'm a physicist. And I think about that, maybe maybe the muon is just this, it just carry more energy, but for some reason too I kind of know that big particles, they're no kind of welcome in the universe. They decay really fast, and I don't know if it's maybe out of a big explosion, or let's say like solar wind, and that gets into our atmosphere and just blow a lot of that energy, and then suddenly we have muons, but it's just way too much energy together, and then they disperse and create the actual particles. Is it kind of like that actually? Have you guys think about that? Maybe it's well, yeah, they're not just a different thing. It's just I don't know. Let's say photons. You're right. Like you have this beam of light, this particle, this photon, but it is a photon. It doesn't change. It's just one of the it's light. Mm-hmm. But then you have different ranges of those photons, mm-hmm. like gamma ray, X-ray, mm-hmm. whatever. That you have that whole thing. Could that be it? Could that be we have just an electron. The difference is that one have way too much energy that the universe cannot handle, and then split it apart into an electron and couple neutrinos. Isn't it like that?
I don't think you have to pretend that you're a physicist. You are a physicist. I mean, you are thinking about the universe and coming up with ideas and asking questions. That's all being a physicist is. I like to think that we're all sort of physicists. If you have any interest in understanding the universe and you can ask these kind of questions, then you're definitely a physicist. So the short answer to your question is we don't know what the relationship is. And we see that muons are created when you do have more energy. You're right, they're heavier, and they tend to decay into electrons. They don't last very long. You can't have a pile of muons. They last for microseconds, and then they turn into electrons and a bunch of neutrinos. And you're right, so heavy things don't last very long. It's like the universe likes to relax from heavy things down to light things. It goes down the ladder. Now, is there a relationship between muons and electrons that's similar to the relationship between X-rays, gamma rays, and other photons? It's a really cool idea. So far, we haven't seen a pattern, and we look at the masses, like the electron mass, the muon mass, and the tau mass, and those are three numbers, but there's not like there's an equal spacing. It's not like the pattern makes sense. And the other thing is we have more clues. Like the other particles we talked about, the up quark and the down quark, each of those also has two heavy cousins. So like the electron has two heavy cousins, so does the up quark. They're called the charm and the top quarks. The down quark has two heavy cousins. So you might immediately think, oh, okay, let's look at the pattern of the masses and see if it's the same relationship, right, in the electrons as it is in the ups quarks and the down quarks. But it's not. It's totally different. There's no pattern there that we can see. So it would be great if there was some structure, right? If there was each one was twice the next one, which was then twice the next one, or a power of 3 or something. But there's no pattern there we can discern. And we think we know how these particles get mass. Maybe you've heard of the Higgs boson. We can talk about that a little bit. They get their mass from the Higgs boson, but we don't know why some of them get a lot and some of them get a little. So it's a huge unanswered question. We just look at this table of numbers and we have no clue why these numbers are what they are. We think there must be a reason, right? You don't
Mm-hmm.
like to look at the universe and say, just random numbers. There's almost
Yeah.
always a reason, right? The physicist in you wants to know why. We just don't know. I don't know. You don't know. Nobody knows.
Yeah, yeah. Well, that's another part. Let's talk about quarks, because to me those are like the craziest particles. Because yeah, because we kind of understand how particles kind of get their energy, kind of
Mm-hmm.
in some cases, or at least we have some theories about that. But what about quirks? Like these guys cannot be by themselves apparently, and out of nowhere, if you try to pull them apart as much as you can, then suddenly out of nowhere, like a cell is multiplying or something, they just create a partner. How does that work?
It's insane. Yeah, quarks are really weird little particles. And quarks are different from electrons in that they feel another force. Like, of the forces in nature, there's gravity, and everything that has mass feels gravity. There's electromagnetism, and everything that has electric charge, positive or negative, will feel that force. Then there's the weak nuclear force, which we can talk about later. And then there's the strong nuclear force, and this is the one that like holds the nucleus together. It's the reason why protons don't push each other away, right? Why does the nucleus
Hmm.
not blow up? It's all positive charged protons and some neutrons. Why don't they push each other apart? The answer is the strong force. The strong force,
Hmm.
super duper strong, like really well named, much more powerful than electromagnetism. And it's also what's holding the proton together. Not only does it hold the protons, the different protons together into a nucleus, it makes one proton into a particle. And a proton is three quarks all tied together. But the absolute weirdest thing about the strong force is that it's not like electromagnetism that has two charges, like a plus and a minus. It has three, right?
Hmm.
And you might be like, what plus, minus, and what else, right?
What
Well, you
else?
have to
Yeah.
sort of bend your mind and have an axis with three directions on it. And so, because that's like doesn't work very well mathematically, instead we think of it artistically. So we think of them as
Hmm.
colors. So there's a red direction, a blue direction, and a green direction. And in order to get something to add up to have no force, like the equivalent of zero electric charge, you have to add up one red, one green, and one blue. That adds up to white, which is no effective charge. So you can get this triplet of quarks, like every proton in your body has three quarks in it. One is red, one is green, one is blue. And that's why they're neutral. They don't have any leftover strong force, but they're tied together really, really powerfully. Um, and the other strange thing about the strong force, other than having three charges instead of two, is just as you said, it doesn't let the quarks be by themselves. It's so powerful, but as you pull the quarks apart, it actually gets more powerful. Like electromagnetism, if you have two charges, as you pull them apart, it gets weaker, like gravity,
Hmm.
right?
Hmm.
Like you can feel the Earth's gravity pretty strongly, but you're not really feeling Jupiter's gravity or stars really far away really powerfully. There is some gravity there, but you don't really feel it. The strong force is the opposite. As you get further away, it gets more powerful, which is crazy, right? And it means that if you try to pull two quarks apart, you're creating a lot of energy in that bond. As they get further and further apart, there's an enormous amount of energy. And the universe doesn't like to have that much just like energy flowing in that system. And so it creates new quarks between them or it turns that energy into matter and it creates new quarks to balance it out. It's like tension in the universe and it wants to relax it by canceling out those charges.
Wow. So pretty much, quarks do really need a like a balance, and they will create their own balance if you try to take them apart. That's pretty much what it is. Um,
Yeah, because
that's
the strong force is like the opposite of everything you're familiar with. It's just another example of how things at the particle level follow different rules. The rules that you thought were deep and true about the universe um, can sometimes just be like thrown away when it comes down to the particle level. And the rules are just different, and you have to get used to it and accept the fact that our experience here is not typical or representative, and that if you really want to understand the universe, you have to sort of let go of a lot of ideas you thought were real and true and accept something totally new. But that's also sort of wonderful.
it is beautiful. Every time I read about this, it's just that you kind of need a little level of understanding so you don't lose your mind when you're reading or talking about these things. Because at some point, yes, at some point you understand and it kind of makes sense. And it's kind of, oh, yeah, that's kind of obvious. But at the beginning, when you start reading, it's like, what? What? Because since we're talking about the nucleus right now, like the strong force pretty much what keep that nucleus
Mm-hmm.
together.
Mm-hmm.
One thing that I don't understand too well is like the weak force. What is actually like the WC bosons? Like I know they work kind of like a decay of the particles or something like that, decay of the nucleus, but I don't really understand that part in there.
Yeah, the weak nuclear force is amazing because it turns out that it's actually part of electromagnetism. Like the weak nuclear force, we sometimes used to think of as its own force, but it's actually part of electromagnetism. It's part of a larger force we call electroweak. And just the same way we used to think that electricity and magnetism were totally separate, like 150 years ago, people saw sparks, like, oh, that's electricity. And then people saw magnets, like, that's magnetism. And then people figured out, oh, they're connected. Look, electricity can create magnetism, magnetism can create electricity. These things we thought were separate are actually two sides of the same thing. It's like if you'd only seen the front of an elephant and somebody else had only seen the tail of an elephant, and you're talking to each other about it, and then you discover, oh, wait a second, these are connected, literally. We made that realization about electromagnetism, in the late 1800s, and it's a beautiful insight, right? It shows you how to simplify your understanding of the universe, which is the goal, right? We always want to
Uh-huh.
say, here's all the things we've observed, let's describe them in the simplest way possible. Well, in the 60s, 1960s, somebody realized you can do the same thing, connect the weak nuclear force with electromagnetism. It turns out those are just two sides of an even bigger coin. And the W bosons and the Z bosons are just like the photon, except for some weird reason, they got a lot of mass. So the photon is massless. It travels at the speed of light. It can go through the whole universe without stopping. The Z boson is just like the photon, except it has a lot of mass. It's very heavy. And that's why it's weak, because it can hardly go very far. It lasts a really short amount of time and then it decays. And so, sometime in the very early universe, these particles got mass. In the very early universe, the weak force was not weak, it was just as strong as electromagnetism. And then this symmetry between them broke, and the Higgs boson gave mass to the W and Z bosons, making them very, very weak. It sounds like a biblical story, right? And it chose its favorite children or something. Anyway, it gave those particles mass and made them very weak, and the photons stayed massless. And it turns out that there are four particles in the electroweak force: the photon, the Z, and the two W particles. One of them happens to be massless, and the other three are not. It's an amazing story.
Okay, so it's kind of it's if I understand well, it's kind of like what we talked before. Like for some reason, universe don't like heavy particles, so start
Yeah,
like kind of decaying them. Oh,
yeah,
okay.
exactly. And that's
Uh,
why it's very short-lived. Like you can't feel the weak force unless you're very, very close to something else which feels the weak force. And the consequences are huge. Like there are these particles, neutrinos, which are really weird little particles. And they're weird not because they're rare, they're everywhere, but we can hardly feel them because the only force they feel is the weak force. They don't feel electromagnetism, they don't feel the strong force, they only feel the weak force. And if you hold out your finger, 100 billion neutrinos from the sun pass through your finger every second. So you should be glad that you can't feel them because otherwise they would like shred you and give you
destroy
cancer,
you.
right? They just wanted to be
Destroy you,
destroying
yeah.
us. And the reason they can't feel you is because the only way they can interact with you is through this weak nuclear force, which is super duper weak. And a neutrino, it can go through like 1 light year of lead without even noticing. It passes right through you. Yeah. And it's not
Oh my
because it's small, right? This is not about like avoiding, like, it's not like about slipping between atoms. These atoms just don't talk to each other. It's like, two people today walking on a path in social distancing, right? They just try not to get near each other. They just pass right through each other as if they're not even there. Um, and so
So
there's this other view of the universe, like where there's all this stuff happening that you cannot see, right? There's neutrinos streaming through us all the time, everywhere, and you can't even see them.
so it should be any type of quantum field that works with like for example that neutrinos that we know about at all.
The only field that can talk to the neutrinos is the weak nuclear force. Yeah, so the field of
That's
the
it.
W and the Z, and that's it as far as we know.
Mm,
So it's pretty weird. And the sun makes a lot of these because you make neutrinos when you do fusion, and a
mhm.
lot of the energy of the sun actually comes out in neutrinos. And so if we could like capture the energy of neutrinos, it would solve all of our energy problems. There's like energy
Oh,
all around us. You know, if we could only capture it somehow, then we would have as much energy as we ever needed. But it's inaccessible to us. You know, it just flies right through.
well. All right, then let's talk about that part because every time well, in my case, I try to understand because I was even reading the Sean Carroll last book called Something Deeply Hidden. I'm
Mm-hmm.
almost over with it. And at some point, he's talking about the quantum fields. And in the quantum fields, he's talking about like a Everetarian kind of theory. And at some point, you kind of realize like, okay, there's not actually particles. There's supposed to be like some kind of reaction or interaction, like wave growing out of that
Mm-hmm.
field. But
Mm-hmm.
still, we understand and it works when we use particles to explain stuff. But at the same time, um, what are actually, like, can we just use both of them and they will both work? Or actually, particles are points in space, or they're just reactions in that field?
It's a totally great question. Like, what's actually going on, right? What is really happening down there? The short answer is that these things are not particles, they're not points in space, they're not waves, they're not wiggles in quantum fields. They're something totally new and weird. And in some cases, some of these ideas work. They help us think about these things, they help us do calculations to predict what they will do, but none of them describe completely what's happening. Because what's happening is something that's totally alien to our experience. It's different from anything you've ever seen or experienced, right? Think about sort of philosophically, what are we doing with physics? We're trying to
Hmm.
understand the unknown, but we can only understand it in terms of the known, right? It's like if I give you a new flavor of ice cream, you'd be like, it's kind of like chocolate, it's a little bit like coffee, maybe with a hint of, whatever, cherry. You're expressing in terms of the things you know, right? Which is all you can do. You
Uh-huh.
can't describe a new flavor in terms of like what, right? So we discover these new weird objects, photons and other little things. What are they? Well, sometimes talking about them like a particle makes sense. It's flying through empty space, like you would imagine a ball would if you threw it. Sometimes talking about them like waves from quantum wave functions makes sense. Like they interfere with each other, right? Particles can't do that. Sometimes talking about them as wiggles in a quantum field makes sense because things get created and destroyed, and it makes more sense to talk about them as like energy oscillating in a field rather than a particle disappearing, which is sort of weird. So sometimes one picture makes sense, sometimes another picture makes sense. None of it is real, none of it is true. That's why I'm desperate to meet alien physicists, because alien physicists will have other totally crazy ideas for what's going on down there. And when we first hear them, we'll go like, "What? That makes no sense at all." And then eventually we'll be like, "Oh, I see. You're thinking about it this way. I never thought about that. That's actually kind of a deep insight." And then maybe together somehow we'll sort of triangulate what's going on down there. But in the end, I don't know if we ever can really know, because the quantum realm is just different. It's just different from anything we can understand. So I'm not sure our brains are capable of really experiencing it in a way that you can experience your life and
Hmm.
love and the things that you grew up understanding.
Yeah, yeah. It's there's like a lot of theories, and most of them make a lot of sense. But we can keep going down and down and down all the way to like strings, and it's even deeper there. And we probably would have so much more questions.
And
But
even if we had that theory, like let's say we had string theory and it
mhm,
worked and we could
yeah,
calculate stuff, does that mean that there really are strings? Like strings are
yeah.
there doing that vibration? Or does that just mean this is a way we can think about it that lets us do calculations that predict experiments? That's a philosophy question, right? It's like, is the universe actually out there, and are my models real, or are they just things I calculate? And I don't know the answer to that. That's the kind of thing you need to smoke a lot of banana peels and then think about.
That's great. All right, let's get into one thing that I'm really excited about it. I know you have worked in the LHC, the
Yep.
Large Hadron Collider. How does that work?
You take a
I mean,
really big rubber band and you put a proton in it. No, it's a lot of fun. I feel really lucky to get to work at the Large Hadron Collider. When I go there, I feel like I'm in a science fiction movie. I mean, we have these devices that are like huge cubes of electronics that are like 4 stories high, and the way that people talk about things and accelerating particles to the speed of light, it feels like science fiction, but it's real, and it amazes me what humanity can do. It's like you see a beautiful bridge like the Golden Gate Bridge, and you're like, wow, look what people can do that's so much more than one person. No one person could have built that bridge, but together we've accomplished something incredible. That's how I feel about the Large Hadron Collider. Like, wow, look what humanity can do. And the way it works is that we smash particles together, and that means that we take a bunch of particles. The biggest misconception is that we're smashing individual particles, that we're like, okay, Bob the photon and Sally the proton, get in the collider, we're going to smash it together, it's your turn. That doesn't work because the particles are so small that they basically never hate each other, right? Even if like you and your friends shot guns at each other, not recommended, what are the chances that the bullets would hit, right? None. You just shoot each other. So these protons are much, much, much smaller, so the chances of them hitting is very small. So instead what we do is we get a little gas of protons, like 10 to the 12, like a trillion protons, and we shoot it at another trillion protons going the other way. And they pass through each other, and a few of them sometimes interact. Sometimes they pass through, you get no interactions. Sometimes you get 10 interactions. Sometimes you get 1 or 2. And we start off with just hydrogen, and we heat it up so the electron leaves, and we have protons. And then we give those a little push using electricity, right? And then we just give it a bigger push and a bigger push and a bigger push. And we actually have a series of these accelerators, like smaller and then bigger and bigger and bigger, till finally they're going fast enough to get injected into the actual big one, the Large Hadron Collider. And you have to be going the right speed. You can't just put cold protons in there, because there's a connection between the size of the machine and the strength of the magnets. Like a proton will zoom along in a straight line. If you want it to go in a circle, you got to bend it with a magnet. But then you have to get the magnet strength just right so the proton doesn't like run into the wall, right? So you have to be going at the right speed and have the magnet strength just right. So you put them in there, and they're swimming around, and there's actually 2 of these, and they're going opposite directions. And then at a certain place around the ring, they collide the beams, and they pass through each other. And around that place, we've surrounded with a bunch of electronics, basically a big digital camera to take a picture of this collision. And that's the basics of how it works. And if you're interested, I can tell you about how the detectors work and how we see it.
wow, 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 wow. Let me ask you, is it, with like the Higgs boson, we kind of knew that it kind of exists and we were trying to find it. Is it any other particle that we have in any other theory or any hypothesis that we're like, okay, if we find other than the graviton,
Mm-hmm.
is there another particle that you guys are working right now? Like, okay, to actually make this hypothesis work, we probably need to find this other particle. Is it
Mm-hmm.
any
Mm-hmm.
other new particles you guys are looking for?
Well, the one that I'm specifically looking for is dark matter. Like, we know that dark matter is real. We know it's out there. We know it's stuff. We know it feels gravity. That's about it. And one of the deepest questions is like, what is it made out of? I'm made out of quarks and electrons, so are you. Is dark matter made out of another kind of particle? We know dark matter is not made out of quarks and electrons. Is it made out of some new particle we've never seen before? Is it made out of 10 different kinds of particles we've never seen before? So one way to try to study that is to make dark matter at the Large Hadron Collider. We smash protons together, and we hope that sometimes, 1 every million, 1 every billion, 1 every trillion collisions, we might create dark matter. And then we'd actually have some in the lab, and we could study it. So my research group is trying to create dark matter and figure out what it is. Like, is it a particle? Is it something else? We don't even know.
But that's something interesting because we know dark matter doesn't interact, at least with the electromagnetic force and things like that. So we know it feels gravity, or at least it kind of works with gravity because there is stuff,
Mm-hmm. Mm-hmm.
moving around that, and it helps in the corners of the galaxies that the stars and galaxies don't fly away. So
Mm-hmm.
we know it's a certain, it does feel gravity. But how do we how are we gonna know if you guys actually create dark matter? Because we cannot see it at all, or it doesn't interact with electromagnetic force. How
You're totally right. We could create dark matter in the lab, and then how would we know if we have? You're right. We can't take a picture of it. We can't see it in the usual way. But we can tell sometimes when we've made something invisible. And here's how is that we smash particles together and they're sort of moving along a line. So there's like a line the beam follows. And stuff flies out sideways, right? And because of conservation momentum, we know that the stuff that flies out to the left has to balance the stuff that flies out to the right. Because in the initial collision, there was no motion to the left or the right, it was just along this beam line. So if we make something invisible, then what we see is that we see stuff flying out on one side and nothing flying out on the other side. And we think, oh, well, there must have been something there because we believe in conservation of momentum. So, if something is imbalanced, then we suspect there was something invisible there to balance it. And we can't see it directly, we can only see it indirectly. So that's what we're doing is we're smashing particles together and we're looking for collisions that lead to an imbalance where we can't account for all the energy, where some of it must have disappeared into something invisible. And that's the best we can do. And it's,
oh,
if we can do that and we can see it, that would be interesting. But it's not necessarily convincing. Like, if we saw that at the collider, it wouldn't be enough, I think, to claim discovery to say, look, this is dark matter. We have other ways we're looking for dark matter at the same time, and we'd need to see it in different experiments. Like another thing we're doing is we're looking for dark matter that comes from space. We think there's dark matter everywhere. We think it's the Earth is swimming in dark matter. So we have these big experiments underground that where it's just like a huge tank of quiet particles sitting there, and we're hoping dark matter bumps into one of them and one of them wiggles. That's like a really, really hard experiment to do, to watch like a 1 ton tank of xenon and wait for one of them to wiggle. But if that happens, then we think, oh, well, maybe that was dark matter. And if we do experiments at the collider and we see invisible particles being created at the same rate, then we can connect them. We can say, are these the same particles that you saw over there as the ones we made in the collider? So we'll try to sort of triangulate from different directions. But it's pretty tricky. And it might be hopeless. Like you said, dark matter feels gravity. It might not feel any other force. All of these experiments assume that dark matter has some way to interact with our normal matter. It can bump these little atoms in the underground tanks. It can be created from protons. We don't know if that's true. It might be that it doesn't have any interaction with us at all other than gravity, which would make it very difficult to discover what kind of particle it's made out of. But back to your other question, what are we looking for at the Large Hadron Collider? It's a great question. And you asked, what other theories are there that you're trying to figure out? And that's a great way to start. Like, we build this collider, what particles should we look for? Cool. But think about it like, say you were landing on a new planet, right? You sent a spaceship to Mars. You might have some questions like, I'm looking for water, I'm going to look for life. But you wouldn't only look for that, right? You'd explore. You'd be open to surprises. You'd be like, well, let's just look around, right? And not be like, oh, we didn't find water, let's go home. Um, and so that's what we're doing at the Large Hadron Collider is we're exploring. We're saying maybe we'll see dark matter, maybe we'll see supersymmetry, maybe we'll see something crazy and surprising. And my personal like scientific fantasy is to see something bonkers. I want to discover something like the muon, where people are like, what? That doesn't make any sense at all. Come on. Because those moments when you discover something weird and crazy and unexpected, those are the moments when you blow up everything you thought you knew and you're like, okay, let's start again. We have a new big clue as to where the universe works. So what I'm focusing on. We're looking for dark matter, but we're also looking for weird new stuff that we didn't anticipate. And that's the funnest part because any day you could discover something crazy.
Mm-hmm. Mm-hmm. Definitely. Let me ask you, do you think like maybe we do need like a bigger collider? Maybe. I don't know. Because, like, this is my point. Like,
Hmm.
people think that we're going to destroy the world with those collisions, but we have billions and billions of stars just smashing every second. And it's really, I'm pretty sure it's way stronger and we're still alive. But I mean, do you think with a bigger collider that might help? Like, way faster particles colliding? I don't know.
It will definitely help. A bigger collider would let us see smaller things. It would let us see heavier things. It would reveal another layer to the universe. But it's exploration. We don't know what's there. It's like saying, should we
Mm,
go land on this planet? Well, yeah. It could end up just being like boring rocks, or it could like have crazy life forms on it. You just don't know before you go. And so one thing you shouldn't do is like promise and say, well, if you give us $50 billion to build this collider, we will discover dark matter. Well, we don't know. It's research, okay? It's
yeah.
research. It's not corporate profits. It's not like, Microsoft Office where we release the next thing and we know what's going to happen. Like, it's research. And so the question you have to ask is it worth the money? And $50 billion, that's the cost of the next collider, is a lot of money. I mean, think about all
Yeah.
the hot lunches you could buy for poor school students and the books you could buy and the teachers' salaries you could raise, and there's lots of good ways to
Yeah.
spend $50 billion. On the other hand, they just spent $1 trillion saving Wall Street. So I feel
Yeah.
like on one hand it's not that much money, on the other hand it's a lot of money. So it's not really a scientific question. Definitely $50 billion would buy us knowledge about the universe for sure, no question. Is it worth the price tag? That's a political decision. And I mean, if I were in
Yeah.
Congress, I would vote for that. I would also vote to give $50 billion to lots of other science research. Like, I
Mm-hmm.
don't understand why, as a country, we don't spend more on research. Like, our research
Yeah.
budget is tiny compared to what we spend on everything else. And the
I
way
know.
we got here, why are we the richest country in the world? Why do we have the best tech in the world? Why do we have good education and all this stuff? The reason we did that is because we invested in research. All
Yeah.
those advancements came out of basic research. It's such a great investment. I don't know why we're not multiplying our research budget by a factor of 10. So, seriously,
Right.
20. 20.
Yeah.
I mean,
But that's the thing. I'm sorry to interrupt you, but yeah, it's like definitely crazy when people see like NASA doing all this stuff, and it's crazy that people don't realize that's like 0.45 at the budget of the federal budget. It's not even like half percent of it's not even half percent of 1%,
I know.
and we do a lot of things, and sometimes people believe like, yeah, but education this and that, yeah, that's true, but right now you wouldn't have a cell phone or GPS or whatever if
I
it's not
know.
because NASA
Yeah.
work with all this stuff that make your life easier with the Wi-Fi and etc. etc. So there is a balance, like you said. Like, it is a political question or
Yeah.
decision, but definitely would probably help.
Yeah.
I
Or
have
we should just buy
two.
one less, aircraft carrier or
Hmm.
jet,
Hmm.
and that could fund everything. Anyway, sorry, go ahead.
Yeah. All right, I have a couple more questions. Since you talk about dark matter, uh, what do you guys think, or if it's any theory that I haven't read about it, because pretty much everyone says like we don't know, we don't have an idea. Is it any theory or any particles that maybe we be looking into, like for example gravity? According to Einstein, right, the relativity and special relativity, gravity is like a silk, like something that is physical there, and you can bend and whatever. And we thought like, well, it's gonna be impossible to see gravitational waves, and we have to. But then when you think about like the sheet of space, and then you think about, okay, but this thing is expanding, so it's creating more space, and that's called dark energy.
Hmm.
Uh, what are we doing about that? Do we think it's another kind of particle, or because it kind of come out of nowhere too? I don't
It
know.
kind of came out of nowhere. It's one of my favorite scientific discoveries because they weren't even looking for it. They were trying to figure out how quickly is the universe slowing down its expansion? And then they discovered, oh, it's not slowing down at all. It's expanding faster and faster. It's speeding up. And that blew everybody's minds. And, it's only like 20 something years ago that we learned about this thing, which is the most powerful energy thing in the universe. It's like 2/3 of all the energy in the universe. We just learned about 20 years ago. Like, how could anybody believe that we understand anything, right? So, what are we doing about that? We are scratching our heads and coming up with ideas, and we have no good ideas so far. Like, we have some ideas, but none of them work kind of like at all. And that's, exciting because it means that the right idea is still out there. Somebody's going to think about the right idea to understand how the universe is expanding and why it's expanding. And we don't even know, like, is it expanding at the same rate as it was in the early universe? We have all these measurements that don't actually even make sense with each other. So we're just getting started. We don't know, is it a force? Is it a particle? Is it just a weird manifestation of gravity? Because gravity is something we don't understand, even though Einstein's theory is beautiful and works, and as you say, describes gravitational waves. It doesn't describe things quantum mechanically, and we think the universe is quantum mechanical. So this could be some weird manifestation of a new gravity that we haven't seen before, or it could be something totally different that we don't understand. And I'm looking forward to being part of helping to figure that out, or even just reading about it and understanding the universe at a deeper level. It's wonderful to live in a time of mysteries, I think.
Wow, that's great. That's a great answer, actually. So the last question, because I think out of all the forces, gravity is the one that I love the most. And we believe, yeah, because it's kind of if you have like a book that you want to feel like, I mean, inspired or whatever,
Uh-huh.
would be called gravity. Because, it's like the weakest force, but it's so patient and
Yeah,
create everything.
yeah.
So it's like gravity is the best.
It
I
wins in
know
the end,
people,
right? It wins in
yeah.
the end, yeah.
Exactly. So coming to the part like around the expansion of the universe
Mm-hmm.
and kind of like if it's a weird thing of gravity and we believe like the universe is quantized, uh, what's going on if like if you can explain that, because I know we don't have a good theory, I know that, but can you explain a little bit why we don't understand gravity inside a black hole?
Yeah, well, that's a great question. We don't understand gravity inside a black hole because we can't see inside a black hole, which we're desperate to do. And the reason it's interesting to see inside a black hole is because that's where we think our current theories of gravity fail. Like, we have a theory of gravity, as you say, which describes gravity not as a force, but as like a curvature of space. Like, things with mass bend space, and that changes what sort of the shortest path is, so that it's a curved path instead of a straight line. But we think of everything else in the universe as quantized, and so there's various different approaches to taking gravity and understanding it quantum mechanically. One is to say, well, maybe gravity is a force, and the way it works is by passing these gravitons back and forth. That's one idea. We've never seen gravitons. They might be very hard to spot. So um, that's one idea. But the problem is when you put that idea together and you make a quantum theory of gravity, usually it doesn't work. Like, it fails when gravity gets really, really strong. When I say it fails, I mean, like, you sit down and try to calculate what happens inside a black hole, and it gives you nonsense. It gives you like infinite energy or infinite forces, and that just can't happen. So what we'd like to do is see what's going on inside a black hole, so we can say, okay, that's what we have to get our theory to predict. So we know sort of like what the target is, like what's going on. Because right now, our theory works perfectly. Like, general relativity works perfectly everywhere in space, but we think it fails inside a black hole. Like, inside a black hole, general relativity says that there's a point of infinite density, right? A singularity that creates a black hole. Quantum mechanics says that's impossible. You can't localize a point of space so well to know exactly where it is and how much energy it has. It's impossible. So these two theories disagree about what's happening inside a black hole, but the secret, the answer, is held behind a curtain, right? We can't see it. So that's very frustrating. There's a whole other different approach that says, don't try to turn gravity into a quantum theory. Instead, turn space into a quantum theory. Like, not the forces moving through it, but the space itself. Think of space as made of pixels, right? Like, space is not an infinitely smooth thing where you can be here or there and any place in between. think of it like there's pixels on your screen. There's only a certain number of places you can be. And so instead of quantizing gravity as a force, we quantize space itself. And that's called loop quantum gravity. Crazy ideas. Also has some struggles. Not sure anybody's going to make it work. But, we're just at the beginning of understanding. And if aliens come and could show us how to look inside a black hole, then we could get into a glimpse of what's actually happening there. It might help us figure out what gravity is and why it's the best force in the universe. I totally agree with you.
Thank you. All right, Daniel. This has been a super pleasure. Thank you for your time. Because I have talked with another astrophysicist, but in this case, I have never talked with a particle physicist. And one of the things that I love the most is especially like quantum physics and quantum mechanics, because even though it's a little crazy when we understand these things, it's like I even did a video showing how to make a compass, to point to the North Pole, so we understand that it's something in there like electrons that you push to a certain side and it works. But I want to, in all my chapters, at the end of the chapter, I always bring a book. And I know I'm going to share one book, that is your book, but I want you to share one book for all the listeners. What is your favorite book? It could be like science fictions that I know you like a lot, or science, or whatever book that you want to bring to our listeners tonight.
Well, one of my favorite books about science is a book called What is Real? It's by Adam Becker, and it does a great job of talking about this question like, are things particles? Are they waves? How do you think about them? How do you understand them? What experiments have we done to prove that this is really what's happening? It's a really hard thing to write about, and he's done a really good job. I've also met him. He's a really, really nice guy and a good speaker, so I'm very happy to support his work. So it's called What is Real by Adam Becker, and I totally recommend it to you and to all of your listeners.
Thank you. Thanks a lot. All right, guys. In my side, I have a book that is one of my favorite books. It's called We Have No Idea, A Guide to the Unknown Universe. This book is from Jorge Chan and Daniel Whiteson, that is with us today. I love this book because it explains science in a way that is, at least like for me, that I just want to learn. It explains you what we know, and then why we know that bring us to the questions that what we were missing to explain the rest of it. So look it up, and I believe it's in more than one language now, right? How many languages?
En español también. It's in 24 languages now. It just came out in Hebrew.
Wow, man. I didn't know that. Wow, that's great. That's great. Daniel, this has been a huge pleasure. Thank you. Thank you for giving me your time and everything that you help out with this recording. Do you have any last words to say to...
Well, thank you very much. I love your enthusiasm, and I think the questions of the universe belong to everybody. And that some people think only scientists can think about this stuff, but I feel like they belong to everybody, and everybody can and should think about the big questions of the universe. That's why we're here, to love each other, to appreciate art, to have fun, and to ponder this crazy, bonkers, mysterious, beautiful universe that we live in. So thank you for encouraging everybody to use their brains and think about the universe.
Yeah. Thank you. Yeah, that's kind of the point, because I know there is a lot of English podcasts, and there is a lot of YouTube podcasts talking about science, and there is not a lot of podcasts in Spanish. And I believe like education should be like the biggest part for humans, especially when you learn about these things. You learn like we're so small, so that kind of create a little bit of humbleness on people. I believe that's really important. So that's all I try to do.
Well, thank you very much. And thank you for having me on.
Thank you, Daniel. Bye bye.
Bye bye.
Y para ustedes, esto es curiosidad científica.